So hello everyone. The story for this talk actually starts not far from here, just around a 5-minute walk back at my old university in Vienna, right here where we all are. Me and my colleagues, the two, Martin and Thomas, we were all enrolled in a course called Abstract Machines. And the task of this course, like the project part of it, our teacher told us, or professor I should say, told us to basically make any kind of JIT, any kind of interpreter, whatever you like, just present it at the end of June, so we had like roughly 4 months. And I was basically thinking with them, brainstorming, and I was already very familiar with LLVM. They weren't. But like the most influential, or like one of the more cited papers from our professors was actually a Java virtual machine implementation that he made in, I think, 1995 and has been maintaining ever since. So naturally, what does one do? You go against your professor and try to compete. So this is what basically the product of this whole talk is. So as a basics thing, for these not familiar, which is hopefully not a lot, probably not a lot, what is a JVM? So JVM spelled a Java virtual machine. It's basically the core of this compile once and run anywhere promise that Java has, right? So you have your Java source code, and you compile this Java source code to a class file. And using the JVM, you can then execute this class file. So any platform that has a JVM available to it, you can just ship your class file. They run it on their JVM, it works, hopefully. What is this class file? Well, it's kind of like the minimum translation unit, if we want to use C++ lingo or C lingo, that like results from a Java class being compiled. The interesting part for us is like there's many things within the class files. The methods are the interesting part. And the compile once run anywhere promise basically works by having a bytecode for each method implemented in Java that is then executed. How does this bytecode look like? So here's a very, very basic example of an add method. Java bytecode is very famously a stack-based bytecode. That means the operands to most instructions are done using an operand stack. And additionally, there's local variables. These are used to receive function arguments, but also to be able to do any, to essentially have local storage that is independent of any operations being executed. So here we have a super basic example. We have 4 instructions. The first one is an iLoad 0. So what this does is just loads from the first local variable and pushes it onto the stack. This is in our case A. iLoad 1 loads the second variable, pushes it onto the stack. What the iAdd now does, it consumes 2 values on the stack, pops them, pushes the result onto the stack. iReturn pops it from the stack and returns from the function entirely. Now, on first glance, this might look a bit hard to compile because the operand stack, that sounds very dynamic. It's also completely untyped in Java. This doesn't sound great. Well, luckily, there's a few restrictions on Java virtual machine bytecode. So the first one illustrated here, we have an iconst 0, iLoad 0. And depending on the if EQ skip, it will either jump to the skip label or to the iReturn, or it will fall through to the fconst. So here we would have basically dynamic stack depth depending on the path being taken. This is luckily legal, so we don't have to care about these cases. And this is actually enough for us to allow to pre-compute any types and the depth of the stack at any point within the bytecode stream. Similarly for local variables, here we have a similar case where we are doing either an fstore 0, or not, depending on the control flow again. So this would mean that the type of a local variable is different, and this is also not allowed. So now we can start compiling JVM bytecode. This is like the first step if we want to make a compiler, right? The way this is done is actually very simple if you want to do it badly. You can just take the operand stack and the local variables and create a corresponding alloca in LLVM for each of these. And then each time you just pop or push onto the stack, you actually just load into the corresponding alloca or store into the corresponding alloca. So this would be like the prologue for the function where we allocate and then store all the local variables into the Java local variables. The loads would then just be loads from the local variables, stores into the operand stack. The iAdd is loads from the operand stack, add the actual addition, storing back to the operand stack. So this is rather simple. The return is then just loading and doing an LLVM return. Now, how do we integrate this into ORC JIT? So in ORC, there's this concept of a materialization unit, which is very useful. It essentially allows us to register a custom symbol into the context or the atomic unit they call JIT dilibs, and basically gives us a callback where if the symbol is required, then it will call this materialize function that you can see here, and will ask us to basically provide an object file to it. So this is where we can nicely plug in our JVM compiler that we just made. We do need a bit more of a setup though, because then we have the issue that our JVM bytecode might have calls externally, either to other functions of class files that have already been loaded, or maybe even to class files or class objects that haven't even been loaded yet. So here we have 3 dilibs. In the middle, the Java dilib is basically where we want to register all so far loaded Java objects. Then we have a stubs dilib. So this stubs dilib is where we have like little compile stubs that will, once called and only when called, will actually ask the Java dilib to materialize the symbol. This allows us lazy lookup of only, or like lazy compilation of only compiling any Java virtual machine method that we need once it's called for the very, very first time. Any times afterwards, it simply calls the precompiled one. The external one is a bit more special. So for for the registration, this can actually be done with built-in already upstream methods. So you can just, on the Java method, define our bytecode materialization unit that you saw before. And for the stubs, there's this lazy re-export that essentially says, for any of these symbols, just go look up in the Java dilib once you need it. For the external ones, it's a bit more complicated. So here we use a definition generator. Definition generator, this is a utility in ORC that allows us to essentially like just in time define a symbol once required and do this procedurally. So it's kind of like a last resort callback for if a symbol were not to be found, whether we can materialize it elsewhere. We use this to define a compile callback. The compile callback is just an extra indirection that is only called once the function is actually called, not if the symbol is required. And in this compile callback, we'll do a simple sequence of first loading the class object. When the class object is loaded, it's now registered in the stubs, and in the Java dilib, we'll then do a lookup in the stubs to get the now just loaded implementation and replace the compile callback. So that is basically it for the compilation part. Now, Java is famously a bit more higher level, so we also need a bit of a runtime. Garbage collector, for example. So this is the next thing I want to quickly talk about. So what we did, we implemented a relocating garbage collector. A simple mark and sweep. In the first phase, the mark phase, we just basically go through the stack and use these as our roots and then try to identify all the objects that are still alive, still reachable. In this graph, this is rather simple. We follow AD and all the way to C. So these are our alive objects. All the other ones we can basically say are not alive and empty slots that can be reused. Now we also want to do compaction. So to improve locality and defragment our heap, we want to move objects closer into memory. This is easy in the sense of doing the memory manipulation. This is basically just a mem copy in C, right? But the more difficult part is that we need to redirect all of our pointers. So either when the objects are on the heap, these we have to heap references within an object, we have to redirect those. But more importantly, we need to also redirect our stack references. This is the harder part that requires cooperation from the compiler. So here we have also moved C, and then the reference from D also has to move back to C. And then we're basically done. So we have 2 requirements from the compiler to implement this. We need to first be able to find stack references, so any references on the stack pointing to potentially heap allocated object. And we need to also then be able to mutate these to redirect them after the object has moved. How do we do this? So luckily, there's already support in this for LLVM. This has been implemented by Azul, so I'm sort of basing a lot of my work on them. And this is actually surprisingly simple if you know how. The documentation is not that easy. Basically, we use a reference type. The reference type is in reality just the pointer type with address space 1. We annotate all of our functions with the GC and then the name of a garbage collector. So this system is meant to be extendable upstream, but there's already the core CLR garbage collector that upstream that I thought we can reuse. And then you just need to run a little pass. This pass, it basically creates state points. These state points are any calls where garbage collection may happen and where we need to find and be able to mutate these stack references. As a small example, here I have like a Java method, and we have this call to this comparator in it. And there's this one reference here called alive that is live across the call. So we're using this later, and we need this to be relocated, and the pointer value reloaded after the call if there was a garbage collection. What this pass basically does is it puts it into like a verbose form, where the alive is first noted as needing to be relocated and findable on the stack. And any uses afterwards are explicitly made through this relocation intrinsic. So now how to access these at runtime is basically any of these values in this GC live can be found in a stack map that is generated for us by LLVM. These are in like every object file. We can use a linker plugin in JITLink to then read these stack maps. So JITLink provides this nice object linking layer plugin that has like this modified pass config. And with this modified pass config, we can schedule in the pass where we can read out the stack map. And consuming these now at runtime, when we do stack unwinding, there's 4 different kinds of location where our reference now may be. Either it's a constant, this is rather rare, but it could be like a null pointer that LLVM through optimization found out. It could be in a callee saved register. It could be a direct pointer. This means basically it's a stack allocation, so this doesn't actually occur in our case with the Java, in our Java case. Or it's indirect, meaning that the reference has been spilled to the stack and we need to read it from the stack. Writing is similar. We can do this all with LLVM slip unwind, since this is basically the same unwinding mechanism that C++ exceptions work with. Now, we basically assembled the whole runtime system. Basically assembled a compiler. This was basically the state where we were like at 4 months later in June when we first presented it to our professor. We were very happy, ran Hello World, timed it, and 2 seconds. Pretty bad. So then, I mean, people on Hacker News and like Twitter, they keep on saying that Java is like a slow language. Maybe this is expected behavior, right? No, it doesn't look like it. The normal Java is a lot faster. 0.02 seconds compared to 2 seconds is slight difference. Why is that? Well, basically, just the startup routine, so for Hello World, compiles and runs a lot of Java virtual machine methods, around 462 in our case. If we always use LLVM O3 to compile these, then we're actually spending most of our time compiling and not actually running any of the code that our JIT produces. Now, was the JIT the wrong thing to use? Should we have written an interpreter instead? I mean, maybe, but at the same time, the JIT is not that bad in performance. It's not as great as the OpenJDK, mostly because we don't have inlining due to our lazy symbol lookup. We only ever compile 1 method at a time, and also some other Java-specific optimizations that we just can't do in just LLVM. But nevertheless, an interpreter would never be this close. So what if instead we could just use both an interpreter and an LLVM? So this is great. Mexican philosopher once said, why not both? We have a large choice. We can use an interpreter, low optimization level. What we did, which essentially added an interpreter and used LLVM O3. But now you're kind of complicating your whole VM a lot more. You have 2 execution tiers. And in the case of an interpreter, we even have 2 calling conventions. So what we did? We now have multiple JIT libs. Two stub JIT libs, one that is always used meant to be used using the JIT calling convention, we call it. This is basically just a one-to-one mapping of Java to C type system, how you would imagine it. And the interpreter calling convention, which passes everything as like byte packed in like an int64 array. And these can then now either dispatch to the JIT or the interpreter. We can determine at runtime using the same lazy mechanism. The JIT itself, it links to the JIT CC since it eternally uses the JIT CC. The interpreter itself, when it calls a method, it invokes through the interpreter CC stub. We also have adapters, so if the interpreter calls a method that has been deemed that it should have been run in the JIT, it will just go through an adapter that converts from interpreter calling convention to the JIT calling convention, similar to the other things, to the JIT to interpreter. These on the left, we have like a nice interface called an executor where you can just add and register a method, and the executor is supposed to return a JIT tilib that the stubs then link against, depending on which calling convention they need. So the next question is, okay, we have now a JIT and an interpreter. When do we actually want to use which? So we start off with the interpreter always at the very beginning. This is basically the safe and conservative choice. And once we realize that we need more performance, we do a tier up. The easiest trigger to implement is basically on method invocation. So if a method is called a lot, we can just say, okay, increment the counter. If this goes over a threshold, then just let's switch to the JIT. This is easy to do on method invocation as well, since we still have like just our arguments. We can just forward these through the interpreter calling convention. A bit more complicated is if we want to be in a hot loop. So there's a lot of scenarios where you would start a method, have a hot loop, let's say a convolution operation going over an array of thousands and thousands of elements. You may only notice, or like have a backend, you may only notice after 500 iterations or deem it as optimizable. The way this is implemented, we have like a single package counter per method that is incremented each time we have a branch back in your bytecode stream. This is basically a good or like a rough estimation for a loop counter. And once this threshold is hit, then we just escape to the JIT. So this is also a very important use case. This escape to JIT method is doing a bit of heavy lifting here. How does this actually work? So this is actually a more general mechanism called on-stack replacement. What the on-stack replacement allows us to do is essentially take a method that is currently running, so may it be interpreter, JIT, whatever, and replace it completely with a whole new method while it's still running on the stack. So here we have a small example of a foo function being within the interpreter. And it through transitively calls into some kind of runtime method that implements this on-stack replacement. This on-stack replacement implementation will then create a so-called OSR state. So this is basically the minimum state, enough state required that can be extracted from the frame that should be replaced and transferred to the frame that is replacing it. For the Java virtual machine, this is actually rather easy because you can just use the equivalent of the operand stack and the local variables as defined by the Java virtual machine stack specification. And we then just replace the interpreter frame here with the on-stack replacement frame and inject the on-stack replacement state to initialize the operand stack and the local variables. Compiling this on-stack replacement entry is relatively straightforward. It's basically the same as normal compilation, except that our control flow starts somewhere in the middle of the execution. And we have this small OSR prolog, which is where it basically takes the OSR state that you saw before and initializes all the operand stack and local variables from this OSR state. Now we can not only use this to go from interpreter to JIT, as I shown before, but also back from JIT to interpreter. This allows us to do a lot of nice optimistic optimizations. So as an example here we have a try-catch with exceptions. The idea is basically that like, exceptions are exceptional, right? They shouldn't happen in the usual case. So what we can do is that we just don't generate any code for the catch handler. Instead, what we'll do is that when an exception is thrown, during a call, we will go back to the interpreter and replace the JIT frame with the interpreter frame. To do this, we need to extract the OSR state out of the call, out of the JIT frame. This can be done with these deopt operands over here. These basically, in this case, encode the local variables and the bytecode offset. The last thing we need to do, also, these can be read with the exact same mechanism as the GC live pointer. So these are also encoded within the stack map. Now, the very, very last thing we need to do is install the OSR entry. We, once again, use lib unwind for this. So this is reusing the exact same mechanism as exception handling, where you also basically just set the instruction pointer, set all the callee safe registers. The final part is then just to use forced unwind. This is kind of nice because then it also runs any C++ destructor in between, if you have any native methods in between. And at the final part, then just installs the cursor that we've made up. So that is basically it. As a conclusion, I've basically put up all I've talked about. If any of the things in the talk sounded interesting to you and you want to like actually look at the details and not at the slideware that I've shown, the whole thing is open source and on GitHub. And thank you.
Okay, thank you, Markus. We have about 3 minutes for questions if the audience would like to pose any. There's mics around, or I can head to you.
Great talk. I just had a question. So in Escape to JIT, do you have to perform any like sort of relocation, like when you move your function out of the stack, like for, I don't know if there's like some PC relative operands in the thing you move.
So this can potentially be an issue. There's actually like something that looks like an indirect call in Java. For these, we just don't allow any OSR at all. And these instructions in the Java virtual machine are luckily deprecated, so we don't generate any indirect branches, and so this wouldn't be an issue. Otherwise, it could be, yes.
And is there any branch, like, is there a limit to how far you can jump on your stub from the?
No, the ORC JIT by default uses, I think it's large code model, so they always use 64-bit pointer addresses for everything, and so you don't have enough address space for everything.
Thank you.
Any more questions, please?
Just one note to use of the definition generator in ORC. If you add code from there, I saw you just add a call through stub through the definition generator. There is a built-in mechanism for that in LLVM JIT that uses a predefined call through stub and inserts it as a re-export definition, I think.
I mean, that's a lazy re-export you're talking about, right?
Yeah.
Well, this isn't the compile callback that I needs to like execute arbitrary code to load the class object, and then it can replace it. So we're doing sort of the same thing as the lazy re-export, except we don't even have the symbol yet that we are about that it should be looking up.
All right. You want to customize. You want a custom call through stub.
Basically.
Okay. All right. Thanks.
Any more? I just one quick question myself. So I haven't really worked with the JIT, but normally I avoid 03 due to its unpredictability and the overheading compile time. Mm-hmm. Is there a reason you've picked 03 for the LLVM JIT over 02 in this instance? Oh,
not really, no. It was mostly because we definitely couldn't compete on compile time. This LLVM is famously slow. So the idea behind using 02 or 03, it's minor difference in that sense, was mainly to be able to compete in something, which would be code generation. So you can make like very minor examples where like LLVM can vectorize better, for example, but these all have to be in a single method.
Okay, excellent. Thank you. I'd like to ask...
I just have a final question.
Yeah, please.
What's the performance with your interpret, like this hybrid approach, like interpret plus JIT?
So good question. So for the hello world, for example, the whole runtime drops down to like 0.4 seconds. So 5 times faster. The main overhead's still remaining compared to like normal Java. So normal Java has two things. They have parallel class loading, so they multi-thread any class loading. So it's actually quite IO dominated at that point. And they also have like a cache mechanism where they basically are able to mmap already initialized class objects. We don't have this right now. So yeah, at this point, we're dominated by IO for stuff like Hello World. For one of the benchmarks I've shown, there's like 400x difference between the two in some cases.
Very good. Thank you.
Okay, I'd like to ask the audience to thank the speaker one more time. Sorry, we've run out of time. So, thank you very much.